Chasing the sun, humanity's greatest star quest. The sun is the heartbeat of our solar system, a blazing sphere of plasma so immense that it contains 99.8% of all the mass in our planetary neighborhood. It is the reason Earth exists, the engine behind our seasons, our climate, and even the flickering auroras that dance across polar skies. Yet, despite centuries of study, the sun remains one of the greatest mysteries of modern science. Today, two extraordinary spacecraft, one European, one American, are venturing closer than humanity has ever dared, unlocking secrets that could change how we see not only our own star, but all the stars across the universe. A star under watch for centuries. Long before spacecraft existed, astronomers peered at the sun with rudimentary telescopes, sketching the dark blemishes of sunspots and trying to decipher the rhythm of solar activity. In the 17th century, Galileo himself drew sunspot cycles, laying the groundwork for what we now know as the 11-year solar cycle. Centuries later, observatories across Europe, Asia, and the Americas kept detailed records, tracking the sun's moods like ancient farmers once tracked the changing seasons. One of those places, a Royal Observatory in Brussels, has monitored the sun for over 100 years. Today, it is home to the World Data Center for Sunspots, the global archive that helps scientists piece together how our star has behaved over centuries. This continuity of observation is priceless. But now, instead of simply watching the sun from Earth, we are finally flying into its atmosphere. Solar Orbiter, Europe's star-chasing mission. In 2020, Europe launched the Solar Orbiter, a spacecraft designed to withstand heat and radiation unimaginable on Earth. Using multiple gravity assists from Venus and Earth, it has traveled over 2.5 billion kilometers, settling into an orbit that brings it closer to the Sun than Mercury. On board are 10 scientific instruments, cameras that see in X-ray and ultraviolet light, magnetometers that trace invisible magnetic fields, plasma detectors, and sensors that taste the solar wind directly as it rushes past the spacecraft. What makes Solar Orbiter special is its dual approach. Some instruments look at the sun from a distance, capturing images and spectra. Others feel the local environment, sampling the very particles streaming off the star. When these measurements are combined, scientists can connect cause and effect, linking an eruption on the sun's surface to the gust of solar wind that hits the spacecraft moments later. The images alone are revolutionary. For the first time, we can see the solar corona, the sun's outer atmosphere, at a scale fine enough to spot tiny flickers of energy. These minuscule bursts, invisible until now, may finally explain one of the great paradoxes of solar physics: why the corona is more than 1,000,000 degrees hotter than the sun's visible surface, which is only about 5,500 degrees Celsius. It's as if the air above a campfire is suddenly 1,000 times hotter than the flames themselves, a puzzle that has haunted astronomers for decades. Parker Solar Probe, diving into the fire. While Solar Orbiter observes from a safe distance, NASA's Parker Solar Probe goes where no spacecraft has gone before. Launched in 2018, it is the fastest object ever built by humans, reaching speeds of nearly 700,000 kilometers per hour, fast enough to travel from New York to Tokyo in under a minute. Protected by a cutting-edge carbon composite heat shield, Parker schemes the very edge of the sun's corona, passing within just a few million kilometers of the solar surface. This is not just close, it is unimaginably close. At those distances, the front of the heat shield faces temperatures hot enough to melt steel and aluminum, yet the instruments behind it remain at room temperature. This engineering marvel has allowed Parker to sample the corona directly, crossing a boundary scientists call the Alphane critical surface, the mysterious point where the solar wind breaks free from the sun's grip and blasts into the solar system. Inside this zone, Parker has discovered switchbacks, bizarre kinks in the solar wind where streams of charged particles double back on themselves. Tracing these back to their origin, scientists found they rise from giant magnetic funnels on the sun's surface. These switchbacks may be part of the mechanism that accelerates the solar wind to supersonic speeds. Each discovery is rewriting textbooks that once could only guess at the sun's inner workings. Why it matters for Earth. The sun is not just a glowing ball of plasma in the sky. It is a force that shapes life on Earth every second. Streams of solar wind buffet our planet's magnetic field, creating auroras, but also sometimes threatening satellites, navigation systems, and even power grids. A single massive solar storm could, in theory, disrupt global communications and cost trillions in economic damage. By studying the sun up close, Solar Orbiter and Parker aim to turn guesswork into prediction. If we can identify the birth of a solar storm and track its journey toward Earth, we can protect astronauts, satellites, and electrical systems long before the storm arrives. Space weather forecasting, once a dream, is now becoming a science. New frontiers, the poles of the sun. Another of Solar Orbiter's bold goals is to tilt its orbit so that it can peer over the sun's poles, regions that no spacecraft has ever photographed. These polar zones are critical because they control the star's magnetic field, which flips polarity every 11 years. Understanding the poles could unlock the mysteries of the solar cycle itself, helping us predict when the sun will rage with storms and when it will sleep in quiet minimums. Beyond the sun, clues to the universe. What we learn from our sun reaches far beyond the solar system. Every star in the galaxy lives and dies by the same physics: magnetic fields, plasma flows, stellar winds, and cycles of activity. By finally seeing these processes up close, we gain insight into how stars evolve, how they slow their rotation over time, and how their activity affects the planets that orbit them. This knowledge has profound implications for the search for life elsewhere. A planet bathed in constant solar storms might be stripped of its atmosphere, rendering it lifeless. But a planet with a protective magnetic field, like Earth, could preserve oceans and foster biology. Understanding our sun is, in a very real sense, the key to understanding which exoplanets could host life in distant star systems. A human chapter in a cosmic story. Both spacecraft are only at the beginning of their journeys. Solar Orbiter will keep spiraling closer, performing regular flybys of the sun, each time returning troves of data. Parker will continue to dive deeper into the corona, racing faster with each orbit until it becomes almost a permanent companion of our star. Together, they form the most ambitious effort humanity has ever made to truly touch the sun. And this is just the beginning. As humans prepare to return to the moon and eventually travel to Mars, our survival will depend on knowing how to live with the sun's power. The lessons from these two missions are not just about science. They are about the future of exploration, technology, and even human survival beyond Earth. The sun is no longer just a distant orb that rises and sets. It is a dynamic, living star, one that shapes our world and our destiny. For the first time, we are meeting it face to face. And as we unravel its mysteries, we also take one step closer to answering the most profound question of all. If life can thrive under this star, could it thrive beneath another?